Hey, I'm Iman, and today we're going to talk about 5 misconceptions that people have about science. Not so much a misconception, it might be a lack of understanding about why it happens. So the first thing we're going to be looking at is rockets, and this idea that rockets need to go fast. So we can observe that rockets are moving fast in order to take off and go into orbit. But why is that? So in order to explain that, I'm going to do a little demo here behind me. So here I have my swimming pool. This is a tiny little swimming pool. This is a box, okay? And here I have a diving board. So let's imagine I climb up to my diving board and I want to dive into the swimming pool. So I can do a nice little somersault, do a little flip, and do a nice little plonk into the swimming pool, and I'm going to land straight into it. What if I take a run up and leap? So what's going to happen is, in this case, swimming pool's quite small. I'm going to miss the swimming pool entirely, and I'm going to land after it. However, what if I tell you I can run faster? Imagine this is a really long diving board, and I can take an even faster run up. I could go so fast that I miss not only the swimming pool, but the building that the swimming pool is inside of. Okay? So going so fast that way, I just fly straight out and hit the ground after. Now, it doesn't just stop there. What if I tell you that I could run so fast that not only do I miss the swimming pool, the building, but I miss the entire Earth? Yes, sounds weird, but that is what would happen. Remember, the Earth is a sphere. This one's not a very good one, but it's a sphere. So if I'm running so fast this way, I can miss the entire Earth and just keep falling and falling. Gravity is pulling me down, but I'm just missing it because of the curvature of the Earth. Now that speed is known as escape velocity, and that's the reason that the rockets have to be traveling so fast. They need to reach that speed because when they do, they are what's called in orbit. They're continuing to fall, but never hitting the Earth. They keep missing the Earth. So escape velocity is very important because what it tells us is that you have to reach a certain speed, and once you've reached that speed, you don't need any more force. And that speed on Earth is around 11 kilometers per second. So if you're traveling at that speed, you don't need to push anymore. Once you've reached that speed, you can just coast. You can turn your engines off and just coast. Continue moving out. Or if you're orbiting, continue orbiting. In a rocket, we could turn the rockets on slowly and slowly move our way up, and then eventually far, far further away from, say, where the International Space Station is orbiting, we could escape the Earth's gravitational field and then be on our way. But that would take a huge amount of fuel. So the quickest way of doing it while using the least amount of fuel is to reach escape velocity, and then you can just shut your engines off and coast and continue. So and you can conserve that fuel for later, or if you don't have much fuel, that's all you need. So escape velocity is very important there. Okay, so another misconception that we have, and this as well has to do with rockets and space, is that rockets push off the air to get them to move. And that's simply not true. Even here on Earth, where there is a lot of air, when the rocket is taking off, it's not pushing against the air. So, if you can imagine that we are in the middle of space, and for argument's sake, let's say we're far away from any planet, there's no gravity, nothing, and I just plonk you with your spacesuit in the middle of space, and I ask you to move. move from one location to another. Can you do it? So if I don't give you anything else, the answer is no. You cannot move. You cannot translate your location. So if your center of mass is here, you cannot move to here. You may be able to rotate a little bit in place if you can move your mass in a certain way, move your center of mass. You might be able to rotate, but you won't be able to actually translate and so move from one point to another. However, if you had a mass that you could push against and actually release that mass, then you can move. So, for example, if I gave you a bowling ball, you could hold the bowling ball and you could point the bowling ball, say, that way, and you could push it. And as soon as you let that bowling ball go, that bowling ball will have a velocity that way, a high velocity, and you will have a velocity the opposite way. Every action has an equal and opposite reaction. Granted, you would be going slower because you have a higher mass. So the bowling ball will be traveling faster and you will be traveling slower in the opposite direction. But you can move. Of course, once you let the bowling ball go, you will continue moving and the bowling ball will continue moving and it's gone. So you can't change your direction. If you want to do that, you would have to have another mass, another bowling ball, whatever that mass might be. So, in space, when a rocket is wanting to move, it needs to bring its reaction mass with it. So in most cases, that reaction mass is fuel. So the rocket has fuel on board, and just like tiny little bowling balls, it's throwing out those molecules of the gas, which makes up the fuel, out one end, and the rocket can move in the opposite direction. Point that thruster, you can get directionality then. You can actually start moving around. But once you've run out of that fuel, well then, you cannot move. So that is the reason that a rocket is so big. Most of it, 90% of it, is fuel. Only a small bit of it, the payload, is actually getting up out into orbit. Now, granted, most of that fuel is actually to reach escape velocity. It's actually to get the big massive rocket off the Earth fighting against gravity and pushing against our thick atmosphere. Once it gets past that, then it doesn't actually need very much fuel to move when it's in space. So it's not pushing against the air, it's pushing against the fuel that's coming out the back of the rocket. All right, so third misconception is around the idea of cold. So there's this misconception that you can have a source of cold, and the truth is you cannot. You cannot create cold. And you'll probably say, but Iman, I can go to my freezer, I can open it up, I can pull out an ice cube. It's cold in there. The freezer is creating cold. It's a source of cold. No. So in the case of the freezer, what it's doing is it's moving heat. So it's moving heat from within the freezer to outside the freezer. Go to the back of the freezer and put your hand on there and you'll realize that it's hot. So it's actually taking heat that's used to be inside the freezer and it's moving it out. And it uses a device known as a heat pump. And so a heat pump, in terms of just classical refrigeration, uses the idea of compression and expansion of a working fluid, a gas, it's a refrigerant. And when you compress that gas, it heats it up. And when you expand that gas, it actually cools down because of the vibrations of the molecules. So being able to compress the gas in one area, expand the gas in another area, and let air move through and exchange heat through a heat exchanger. That's the process. But it all is working with heat. You're just moving heat from one area to another. In the case of the refrigerator, or the freezer, it's moving heat from inside of it to the back of it. In the case of an air conditioner, the same thing is happening. The outdoor unit is getting hotter and the indoor unit is getting colder. But that requires energy, and actually it's not very efficient. So it produces more heat. And so that's why if you had a room full of fridges, it would actually be very, very hot inside the room because all the machinery is working and releasing heat out into the environment. Yes, inside each of the freezers are cold, but the entire room is actually much hotter. So, fourth misconception actually is sort of related or has some interplay with what we just talked about here, where there's no source of cold. And that is the idea that suction exists. And you might say, what on earth are you talking about? Obviously suction exists. But I can assure you that it doesn't. This idea of suction, that something is able to suck something onto something else, and the suction is the source of the force, is incorrect. So here I have a vacuum cleaner which I have removed the long tube from just so you can see it here. But this whole vacuum cleaner seems to suck, right? It takes debris up into it and moves it up. So we say, yes, the suction is occurring here, and that is what's pulling the material up into the vacuum. But that is not actually the case. When I turn this vacuum on, I can feel suction. However, when I put my hand here, I can see that air is actually blowing out of the other side of the vacuum. So what's happening is the fan blade inside the vacuum, the impeller, is pushing air away from it. Just like when you're standing in front of a fan, you can feel that air is being pushed towards you. As the air is being pushed out, there is a lower pressure region behind. There is less air behind the impeller blade. What happens is the air from outside, which is the ambient air, goes in to fill that void, because things like to move from a high pressure region to a low pressure region. So it's actually the outside air that's pushing in and up into the vacuum cleaner. So when you're vacuuming your floor, it's actually the outside air that's pushing all that dust into the vacuum cleaner. There is no source of vacuum that's actually sucking. It's the atmosphere that's pushing. And that's why if you were to try and vacuum in a room without air, which I do not recommend you do that, but if you try to do that, nothing would happen because there's no air in the room. There is nothing to push that dust up into the vacuum, okay? Same thing with a suction cup. When you push a suction cup down onto a surface, you're pushing that air out through the rubber, okay? And then the suction cup, the volume of the suction cup reduces, and there becomes a seal, and air is trying to get in to the suction cup from around. And when you're pulling it up and you're pushing against something, you feel that suction? No. What you're feeling is the atmosphere on the outside pushing back down on the suction cup. And it's a very strong force that you're pushing against because the atmosphere is very heavy. We're talking about on top of everyone that lives around sea level, we are talking about a force equal to 14 pounds per square inch. So it doesn't sound like much, but when you take a bigger area, that is a lot of force that's pushing down on you. So when you're, say, just sitting on the floor and there's a nice circle around about this big around you, there is 10 kilometers of air above you. And that air has a weight, and that weight is pushing down on you. It's actually 10 tons of force around that area here, because that's 14 psi over a large area is 10 tons of force. So it's a huge amount of force. Of course, the bigger the surface, the higher the force. So if the bigger the suction cup, the harder it is to pull. So what you're pulling against when you're trying to, say, you're lifting up a table with a suction cup, you're not lifting the weight of the table. You're lifting the weight of the air above the suction cup. And of course, because there's no air inside the suction cup, or very little, the atmosphere actually pushes on the table as well. And it can cause the table to lift as long as the pressure is enough to maintain that weight. All right, great. Fifth misconception, and this one doesn't really seem like a misconception when you hear it, because, well, everybody knows it to be true. But it's the idea that fish cannot breathe in air, okay? Just like humans cannot breathe underwater. Now, there is validity to this. You take a fish out of the water and it struggles to breathe and then it dies, unfortunately. But the reason for this is very misunderstood. You see, we have lungs, and our lungs are designed to take in oxygen from the air. However, fish have gills, and gills are designed to take oxygen out of water. Now, water, another misconception some people think of is, where do fish get that oxygen from? Well, it comes from the O in H2O. No, that oxygen is very, very strongly bound to the hydrogen, and it takes a lot of energy to release that oxygen. So that is not where the fish is getting the oxygen from. The fish is getting the oxygen from dissolved gas in the water. So it's oxygen that's dissolved in the water, but it's still a gas. So fish are still breathing and exchanging gas, just like we do. When we breathe in air, air goes into our lungs and it goes into the surface of the lung and it exchanges through a membrane. The same thing is happening with fish and in their gills. However, something very interesting happens with gills. I have some water, and you can think of a fish's gills like these sheets of paper towel, and they sort of look like that. And the reason they need this shape is because the amount of dissolved oxygen inside water is much, much less than the amount of oxygen that we actually have available to us in the air. So the fish need a mechanism to extract a lot more oxygen than we can with our lungs. So just like a lot of things in biology, they leverage the idea of surface area. So each part of the gill is a very, very, very thin membrane like this, okay? And it's utilizing a lot of surface area on both sides. And there's many, many millions of these membranes all the way around, bunched up like this. And when the water flows through this membrane, the diffusion happens. And carbon dioxide goes out and oxygen goes in, just like it does with our lungs, but at a much, much higher rate because there's much less oxygen available. Now, here's the problem. You can see that these are all spread out like that, and now they're in the air. You can diffuse across, okay, that'd work. However, if I now take this gill and I dunk it in some water, look what happens now. Can see this? Dry it off a little bit. It's all clumped together. Air cannot go through that. It's all stuck together. Okay? So that is what happens when a fish is removed from water. The gills all clump together like that and air cannot pass through. Whereas when they're in the water, they can move around, and the pressure of the water and the viscosity of the water, because the water is thick, it can push those gills apart, flow between them, and get that exchange. So if you could take the gills when a fish is out of water and say you could open them up, each of those membranes up, or you could push the air through it so it is strong enough to pull them apart, then the fish would be able to breathe, because it's the same gas exchange that's happening in our lungs. It's just the anatomy of the gill restricts the movement of the gas because it's structured to work with water flowing through, and water is much more viscous. So those are just a handful of misconceptions, and there's millions and millions more of them that we experience every day, and we don't really think much about them because on the surface, doesn't really mean much. But being able to use a little bit of understanding and a little bit of scientific rigor lets us delve a little bit deeper and really expose a lot of these misconceptions. So I hope you learned something today. Please like and subscribe, and as always, dream big and make it happen.